Hey guys, so in this video we are going to be talking about operators. And as you can see, I've got some functions out here, right? And um when I'm introducing operators, I want to start by introducing them in terms of functions. And then we will go and generalize our idea of operators into, the vectors that we've been using in quantum mechanics. So we're going to get back to that. Um, but to start with, right, an operator, so I've got this operator Q hat over here. And this hat just means it's an operator, right? In quantum mechanics, we've been using, the bra vectors and ket vectors to represent unit vectors, right? So here, right, we don't really need um, a we don't need these hats to represent unit vectors. In quantum mechanics, generally these hats will represent operators. And what I have here is the operator acting on some function f of x will give me another function g of x, right? Put in a function, I operate on that function with an operator, I get a new function, right? And so let's look at a few examples of operators here. So I've got 5 examples that we're going to look at. So the first one is d hat. D hat acting on some function f of x. This will just give us f prime of x, right? And another way of writing this is d hat is defined as the derivative, right? The derivative is an operator. I give it some function f of x and it gives me another function in return, f prime of x. So for example, if I take some function like x squared, right? I take the derivative, d hat on x squared is going to give us 2x, right? So here's one function of x, here's another function of x, here's another function, right? So that's sort of how an operator works. So here's a few more examples. Let's take s hat. S hat on some function f of x is going to give us f of x squared, right? And so, for example, if f of x is, let's take the example of x squared again, right? S hat on f of x will give us x to the fourth, right? So I put in a function, I get out a new function. Let's try a3 hat. And if I operate on f of x with a sub 3 hat, this is going to give me f of x plus 3. And we can stick with that example that I've had of x squared, right? Well, if I put in x squared, I get x squared plus 3. Even if I put in like a constant, right? Remember, constant is still a function, right? It's a constant function. So if I put in, f of x equals, 7, then a3 hat acting on 7 will give me 10, right? So let's now look at p9 hat. And this one's a particularly fun one. If I operate on some function f of x with p9 hat, this is going to give me 9, no matter what f of x is. So if I do p9 hat of x squared, it's going to give me 9. If I do operate on, 2x cubed plus 3x plus 1, it's going to give me 9. No matter what, p9 hat of x, p9 hat operating on some function will give me this function in return, right? G of x equals 9 is a function. We can graph it, right? Takes one function, gives me another function. Lastly, and probably a little less trivially than this, we have 2 hat, right? And 2 hat an f of x, right, is just going to give me 2 times f of x, right? And this is generally a way that we write things. If I have some scalar, right? So C is a scalar. In general, if I have c hat acting on some function, this is just going to give me that scalar times f of x, right? So x squared hat, right, is on f of x will just give me x squared times f of x, right? That's sort of just how we denote this. So the operator of some scalar, particularly constants too, right? 2 hat will just be 2 times 2 hat on f of x will just be 2 times f of x. Okay, so now I'd like to look at what we're going to call linear operators. linear operators. And the definition of a linear operator, there's actually two definitions. Or not two definitions, but two criteria that have to be followed. Both of them have to be followed. If it only follows one, then it is not a linear operator. It has to follow both. Right? So the two criteria are, so L hat, I'll call L hat our linear operator. L hat, a linear operator acting on A plus B, must be L hat acting on A plus, regular parentheses, plus L hat acting on B. And therefore, the other criteria for being a linear operator is if I have some constant times A hat, or some constant times A hat. C is here a constant. Right? This is equal to that constant times L hat acting on A. Right? So we can take a constant out of the operator, and we can expand. We can sort of distribute this operator. So let's look at our 5 different cases and see if they're linear. So to start off with, the d hat, right? Well, it's actually a property of derivatives, right? If I take the derivative of a plus b, or let's do it, these are usually functions, so let's call it f plus g. This is equal to f prime plus g prime, right? And same thing, the derivative of c times some function is equal to c times f prime, right? These are properties of derivatives. So, just by properties of derivatives, this is linear, right? Actually, I'll actually specifically write it out what this is, linear. Right? So, let's look at some of these other ones, right? S hat, right? Well, if I have S hat acting on A plus B, right? This is A plus B quantity squared, right? Which we know is A squared plus B squared plus 2AB. This is not equal to S hat acting on A plus S hat acting on B, right? This is not equal to A squared plus B squared, unless both A and B are 0, but in that case it's trivial. So this is not true. This is not true in general. And same thing with the other one, we can actually show, right, if I have S hat on CA, right, this is C squared times A squared, which is not equal to C times S acting on A times A squared, right? Again, unless C is 1 or 0. But in general, this is not true, right? So the S hat is not linear. And I encourage you to go through the rest of these and try to prove whether they are or are not linear using both definitions. I'll give you the answers here. So if you want to go pause the video and try that. I'm assuming if you've wanted to pause the video and try it, you have. And so the answers here are, this is not linear. This is not linear. Right? And this, right, multiplication is linear, right, if we think about it. 2 times A plus B, right, is 2A plus 2B. 2 times CA is equal to C times 2A. This is the distributive property of multiplication. This is the commutative property of multiplication, or actually I think it's both commutative and associative. So yeah, so that's linear operators. In quantum mechanics, we are going to be dealing with linear operators. We are not going to be dealing with any nonlinear operators in quantum mechanics. But these are still operators. It's just in quantum mechanics we are dealing with linear operators, and you'll see a lot more of why that is in section 5, but for right now you'll sort of take me on this. You'll see linear operators will be very, very useful and important for us. One other thing that linear operators can do, if I just want to combine both of these statements here, right? Say I have a linear combination of things. So say I have, right, L hat acting on a linear combination, which is, right, one constant C1A plus C plus C2B, plus dot dot dot, right? You can have as many terms as you want. You can show pretty easily here, right, that, this is true with 2, but if you think about, L hat on A plus B plus C, hopefully you can see why this would also be L hat on A plus L hat on B plus L hat on C, right? I could prove that too, but I don't think that's extremely important. It should be pretty obvious that that is true, that this will work with more than one, right? And so if we do this, right, if we just look at this, well, this would be, L hat. Let me redo that. This would be L hat on C1A plus L hat on on C2B plus dot dot dot, which would be equal to C1 L hat on A plus C2 L hat on B plus dot dot dot, right? So and sort of get rid of this middle step. That's just to show you the work. But you can see that based on these two, right, a linear operator acting on a linear combination, right, if I have C1A plus C2B plus C3D, I've already used C, right, it would be C1 times L hat A, acting on A plus C2 times L hat acting on B plus C3 times L hat acting on D, etc., etc. Right, so hopefully that makes sense. The other thing, and I'm not going to prove this, I'm going to erase this up here, hopefully you've got it down, is a linear combination of linear operators is linear, right? So I'll just put that down here. So C1 times L1 hat plus C2 times L2 hat is linear. And it turns out you can also do this with C plus C3 times L3 hat plus C4, right? And so you can actually show this just by, you can really just do the grunt work, or the grunt work just by showing that this, right, obeys these properties. I'll leave that to you, or you can just sort of take my word on this, right? And remember, we can add plus C3. And this will also work if C is not only a constant, but just is any scalar. But particularly if it is a constant. So yeah, that is what I have for linear operators. So it looks like we can move on. Hopefully you have this down. Just make sure you get this, that a linear combination of linear operators is linear. However, is best to write that for you. So I'm going to erase this here. Okay, so the question is, right, and I'm going to sort of veer off from operators right now, but I'm going to get back on that really soon. Right, we have these state vectors. Right, I've got this state vector, say, we'll call it psi, right? How do I get information from psi, right? It's some vector, right? How is there a way to actually like sort of extract information from that? Because that's important, right? Figuring out, certain information. And indeed there is, and we're going to do that through operators. So that's just my general introduction of how we're going to be using operators in quantum mechanics. But let's go into the details and see a little bit more. So I'm going to go back to our notation where we have phi sub q. So I'm just going to say phi sub q remember, and this is a quantum state. So in a particle could be in phi sub q. So is the state with the observable big Q equals little q, right? So now I'm going to define some operator q hat. Q hat acting on this state, phi sub q, right? Right, and I'm just going to note here, this is phi q is a state with a definite value of the observable q, right? Remember, a lot of states in quantum mechanics, right, don't have, right, when we send those electrons into that Stern-Gerlach experiment, they're not in a state of definitely being either black or white. They're in a superposition. They have some probability of being black, some probability of being white. So it's a pretty special thing to be in a state with a definite value of some observable, right? And if I act on this vector, the state vector with q hat, I'm going to get a special result. I'm going to get its observable value, q, times the vector itself. Right? And this is a special thing, right? This is not just something that ordinarily happens, right? And just so you're not, thinking, oh, well, this is, pretty obvious. This just means that q hat equals little q, right? No, not actually, because this works in different cases. So I'll show you two different cases here. Q hat acting on phi 1 is going to give us q1 times phi 1, right? But q hat acting on phi 2 is going to give us q2 times phi 2, right? And we're assuming q1 and q2 are not the same, right? Because then these wouldn't be, these wouldn't be distinct state vectors. They'd be referring to the same state. Right? And so this also for, the third state, the fourth state, however many states there are. So this is, right, this is not just multiplication. This is a special property that some operator has a special set of vectors that it does this with. And I'm going to erase this, but you hopefully should have it down, right? So you don't just think this is just multiplication. So this we are going to call our operator. These are our eigenvectors. And this, right, and we'll also call them, because they're also state vectors, we'll call them eigenstates. And this is our eigenvalue. Right? And so for any operator, there is a specific set of eigenvectors or eigenstates, right, that have this special quality, right? If we think back to some of those operators that we talked about before, a lot of them don't have, not for every function, they won't have this special property. Now, I'll give an example quickly here, right? Think about the derivative, right? It is a very special case that the derivative acting on some function, or sorry, should be d by dx. The derivative acting on some function y is going to give us some constant multiple of y, right? This is a very special case. In fact, this is one of the things that we solved with, this is a differential equation that I had mentioned in our video on differential equations. Its solution is a times e to the c x, right? So there's a specific set of functions, right? You might call them the eigenfunctions of the operator d by dx, where its eigenvalue would be the c, right? And this is by no means the general formula. This is a very special case. The derivative operator has a special group of eigenfunctions. Right? Just like an operator will have a special group of eigenvectors. And we'll actually be talking more about the significance of the eigenfunctions of the derivative operator later in this course. Right? And so now that we have this, right, and this is going to be really important. How can we use this? Right? And there's two things. One, I can ask, right, does some function, some state vector psi have an have a definite value of the observable Q, right? And we can use this as a test. Well, all we have to do is do Q hat acting on psi, and if we get some Q times psi, then the answer is yes. If we don't get some multiple of psi, some constant multiple of psi, then we know the answer is no, right? We can use this operator to tell if a function has a definite value of some observable. We can also, say I have some state, say I have some state, phi1, right? And I want to know what is Q1, right? I want to know what Q1 is. Well, I just take the operator, I acted on phi1, and I'll get Q1 times phi1, and boom, I can figure out what Q1 is, right? And I know we don't have a really solid understanding, a solid formulation of what these vectors are and what these operators are. We will eventually get to there so that we'll be able to apply. We are going to call this our eigenvalue equation. Okay. So I'm going to erase this. Hopefully you've got it all down. Perfect. So now what I want to talk about are Hermitian operators. And right, and so the first thing is looking at some operators in terms of inner products, right? So if I have the inner product of A and Q hat acting on B, and I think we talked about a few videos ago how this is not really that a great notation, but it's the one that physicists use a lot, right? Well, this is just a property of inner products and operators that it turns out that this is equal to Q hat dagger, the Hermitian conjugate of Q hat acting on A, inner product with B. And I'll give you a little bit of a baby proof of this. And so what I'll do is I'll work with this side. So this is, right, remember with our kind of bad notation, this is Q dagger acting on A. Remember we talked about that notation, right? This inner product with B, right, times this B ket vector. Right, I don't even need those parentheses there. And again, some algebra with operators gets a little bit mixed up. But right, if you remember our properties of Hermitian conjugates, right? If I have something like, we actually talked about this, if I have Q hat on A, right? This is equal to Q hat dagger times the A bra vector, right? We talked about this a few videos ago, and so this is just Q hat dagger, right? But remember, the daggers cancel out each other, so this is equal to Q hat acting on A times the B ket vector. And now I'm going to be sort of skipping a step here, because it requires a little bit of linear algebra to really understand why we're doing this. And in section 5, I promise we will get to this. But for right now, I need you guys to sort of just accept that this is true. It turns out that this is equal to, right? It doesn't entirely work out that this is Q hat times the inner product of A and B. That just doesn't happen to work. But it is true that we can bring this Q hat over here, and Q hat, this is equal to Q, the A bra vector times Q hat acting on this ket vector B, right? And so this is A Q hat B, and that is our proof, right? So I know I skipped that step. That's a step you're going to have to trust me on. I promise we will definitely come back to this in section 5, but for right now, I need you guys to just go along with this. So I'm going to erase this proof just so we have the statement up here, right?